Hello friends, in last lecture we understand that how the temperature with respect to temperature and pressure, how the viscosity and kinematic viscosity changes. So in this lecture we'll understand the relationship between the velocity gradient and rate of shear deformation. So consider there is a solid wall. This is a wall here, and on that wall there is a fluid which is flowing uh, with a free stream velocity u infinity. So u infinity is the free stream velocity, and there is a boundary layer formation is there due to the no slip condition on the boundary on the rigid wall. So this will discuss in boundary layer theory. So just try to understand that. So at location x, this is location x, this is x axis and this is y axis. At location x, the boundary layer thickness delta is the boundary layer thickness, and this here at this point the velocity of the fluid element, that is u, and on the dy location the velocity is u plus du. So in that region tau not equal to 0, and outside this region this is a non-viscous flow, tau equal to 0. So this is the viscous flow inside the boundary layer, and this is the non-viscous flow outside the boundary layer. So here tau equal to 0, and here there is a no slip condition us, that is equal to 0, u equal to 0. Okay, now let's try to understand that. The suppose just focus on the large view here. Okay, so at point P we know that the P, that is the velocity u, and here what is the distance, u into dt. Dt is the small time dt. Okay, so the distance is u into dt. S equal to vt, we know that. So s equal to vt, v is the velocity and t is the time, so u into dt. And here at q, so this location the velocity is u plus du. So if you multiply into dt, so u dt plus du dt. So what is this distance? So this distance is u dt, and this is distance is u dt, and this distance, that is du dt, du dot dt. So this is the case. So consider this is the angle, that is d phi. Okay, now if you see that is tan phi, that is equal to du dt by dy. So this distance, that is dy. So tan phi, that is equal to du dt by dy. So if the small d phi, if phi is very small, then tan phi, that is equal to d phi. So d phi by dt, so from this equation d phi by dt, that is equal to du by dy. So this du by dy, this is known as velocity gradient, and d phi by dt, this is the rate of shear deformation. Very important. This is the rate of shear deformation, and this is the velocity gradient. So this is the relationship between the rate of shear deformation and velocity gradient. So let's try to solve one question that is very important for GATE, ESC and SSC JEE exam. So the question is that the velocity distribution over a flat plate is given by u equal to 3 by 4 y minus y square, where u is the velocity in meter per second at a distance y above the plate, and dynamic viscosity for the given fluid is 0.84 Newton second per meter square. The shear stress at a location 0.3 meter above the plate is n times the shear stress at a location 0.2 meter. So above the plate. So you have to calculate the value of n would be. So you have to calculate the value of n. So what is given in this question? So given in this question that the shear stress at location 0.3 meter above the plate is n times the shear stress at a location 0.2 meter above the plate. So the value of n would be what? So what is given in this question? Let's try to understand. Let's start to understand this question. So first, given that is u equal to, this is the velocity profile, u equal to so here this is the velocity distribution, this is the velocity distribution, so 3 by 4 y minus y square. So in question the given as 0.3 location wall shear stress, that is equal to n times 0.2 times wall shear stress. So this is shear stress. Okay, so the tau, that is we know that from Newton law of viscosity, mu into du by dy at y equal to 0.3, because this is at location 0.3, that is equal to n times into mu into du by dy at y equal to 0.3. So mu and cancel out in both sides. Okay, so du by dy, so du by dy, if you derivative on u with respect to y, so 3 by 4 minus 2y, y the value 0.3, that is equal to n into 3 by 4 minus 2, what is the value of y? 2 into 0.2. Okay, so from here you can calculate the n, that is 0.428. Okay, so this is our answer. Now determine about boundary layer thickness. If you want to calculate the boundary layer thickness, then what do you have to do? So the boundary condition at tau equal to 0 when y equal to del h. Okay, so del h is the boundary layer thickness when tau equal to 0. So this is the condition. Okay, so this will read in boundary layer theory in details. Just understand this. Tau equal to, we know that tau equal to 0, tau equal to mu into du by dy. So tau equal to 0, this is the boundary condition. Tau equal to 0, that is mu. What is the value of mu? That is given in the question, that is 0.84 into du by dy 3 by 4 minus 2 into delta h. So from here delta h you will be 3 by 8. So from here you can calculate the boundary layer thickness at a particular location. Okay, now let's focus on the Newton's law of viscosity. Okay, so Newton say that tau, that is the shear stress, that is proportional to rate of shear deformation, that is d phi by dt, and tau, we know that d phi by dt, that is equal to du by dy. So tau, that is equal to velocity gradient du by dy. Okay, now tau, that is equal to mu into du by dy. So this is the Newton law of viscosity for 1d, and if there is a 2d, tau equal to xy, that is equal to mu del v by del x plus del u by del y for 2d. Okay, now let's try to again draw the velocity profile on the solid surface. So this is y location, this is dy distance, and this is y2 location. So this is the layer, this is y2 location, and this is the y2 plus dy location. So this is the velocity profile here. So here, that is at y1 location, the consider this is u, so velocity u and u plus du. So here the angle, that is rate of shear deformation d phi by dt, and here the rate of shear deformation, consider this is d phi dash by dt. Okay, so just example, just consider this is 5 meter per second, here u that is equal to 5 meter per second, and this is 8 meter per second, and u dash, that is equal to 15 meter per second, and consider that is u dash plus du, that is 15.5 meter per second. So if you want to calculate the relative velocity between the two layers, so the relative velocity, that is 15.5 minus 15, that is 0.5 meter per second, and here the relative velocity in between this point, that is 8 minus 5, that is 3 meter per second. So you see that here d phi by dt, that is rate of shear deformation, is greater than, in that location is greater than d phi dash by dt. So okay, now when you see that at y decreases, when this y value at y decreases, so d phi by dt is maximum. So y, when y decreases, here the less value, here the large value, and here also large value. So if y is decreases, then this is the y location, this is the y location. At y decreases, d phi by dt increases, and d phi by dt increases means tau increases. Why? Because we know that tau proportional to d phi by dt. Okay, so at y equal to minimum, y minimum means the y equal to 0 tends to 0 or equal to 0, wall shear stress, that is the maximum shear stress is there. Okay, so tau maximum, that is the maximum shear stress, and tw, that is the wall shear stress. Okay, so this is one important question is there. Try to solve this question, very important question. This is my handwritten notes, you can download it from the description, available in the description. Now another there is a small topic is there, that is the no slip condition. So what is no slip phenomena? So when viscous fluid flows over a relatively solid surface, near the solid surface a thin membrane sticks over the surface and occur the same velocity as of the surface is known as the no slip phenomena. This phenomena is associated with the boundary viscous fluid and defined by macroscopic study. So when the viscous fluid flow over the solid surface, so here the viscous fluid flow over the solid surface, near the solid surface, this surface, the velocity of fluid is same as the velocity of the wall. Okay, so this is the no slip phenomena. Remember, this is very very important data. This is very very important concept you have to remember. So just understand that when viscous fluid flow over a relatively solid surface, near the surface a thin membrane sticks over this surface and occurred the same velocity as the surface is known as no slip phenomena. This phenomena is associated with viscous fluid and defined by macroscopic study. And one term you have to remember, terminal velocity, that is v equal to constant velocity. Terminal velocity means constant velocity. If v equal to constant with respect to time, derivative with respect to time, dv by dt, that is equal to 0. So acceleration, that is equal to 0. So this is all about the no slip phenomena. So in next lecture we will understand what is the boundary linear velocity profile assumption. In next lecture we will cover that. Okay, so this is my handwritten notes. You can download it from the description. If you have any query, any doubt, you can ask me in the message. Thank you.